So as you know, in the modern thermal power plants, they mainly consist four circuits. So we can say the whole power plant is divided in the four circuits. One is a coal and ash circuit, second air and gas circuit, feed water and steam flow circuit, cooling water circuit. So now we can study this four circuit with the help of figure, and we can understand the modern layout of the thermal power plant. So now you can see this is the layout of the modern thermal power plant. You can see here the four circuit. The first one is a coal and ash circuit. The second one is a air and flue gas circuit. Third one is a steam and water circuit, and fourth one is a circulating water circuit. So this is mainly four circuit in the thermal power plant. So how the thermal power plant works, we can study over here. So here we know for the combustion, to produce the steam, we required some fuel, and this fuel comes from the coal handling plant. So the fuel which are come outside, it comes to the storage where it is stored as per the requirement. Then after it comes to the coal handling plant, where it is first pulverized. Pulverized means it is converted into powder form, and then it is passes through the boiler. Inside the boiler, with the help of some air which comes from the atmosphere, pass to the air preheater, where its temperature is raised with the help of the flue gases. So this air and coal mixture are come to the boiler and start to combust. So due to the combustion, large amount of heat is generated. This heat passes through the water, feed water. So this water is now converted into steam. So it's have a high temperature and high pressure. Steam is generated inside the boiler. Now it passes through the superheater, whereas temperature and pressure both are raised. In the superheater, the steam is converted into superheated form. So the function of the superheater is to convert the steam up to its high temperature and pressure, or we can say in superheating form. Then after it passes through the main valve and come to the turbine. So turbine is the main part where the steam is expand, and due to the expansion, or we can say the steam which are come outside from the boiler, it expand or strike on the blades. So blades are mounted on the shaft. So blades are rotated, and the blades are rotated, then shaft is rotated and shaft is rotated. So shaft is directly connected with the generator or alternator. So here the electricity is produced. Now the steam which are used inside the turbine, comes outside and passes through the condenser. Inside the condenser, the steam is condensed. Condensed means here the steam is converted into water at constant temperature, because here only the latent heat of the steam is removed. Only latent heat is removed. So we can say there is no temperature change ideally take place in the condenser. Only the phase changes take place. So after the condenser, the steam is converted into water. So here the condensation process is take place with the help of the circulating cooling water, and this circulating cooling water maybe comes from the river or canal where it is available, or maybe your plant is placed on the river front, then it is possible. But if there is no availability of such a resources at that time, for the cooling purpose the cooling tower is required, because the water, circulating water, is come inside the condenser where it is absorb the heat from the steam and it's become hot. So when it is come outside, it become hot. So we can't circulate this water continuously. So we require to cool down it for next circulation. So here inside the cooling tower, this water is cooled down with the help of air, atmospheric air, and then after it is passes through this circulating circuit. So here the water we can reuse with the help of the cooling tower. So this is the function of the cooling tower, is to condense the circulating water which use in the condenser. Now the steam which are condensed inside the condenser, it is extracted by extracting pump, and then it is passed through the LP heater and HP heater. So what is the function of HP heater and LP heater? So LP heater and HP heater is increase the temperature of feed water which are comes from the condenser, and the LP and HP heater, how they are work. So here the LP heater and HP heater both increase the temperature of feed water with the help of the steam which are extracted from the different layer of the turbine. So here we can say in the high pressure turbine the steam is extracted and it is used to increase the temperature of water in the HP heater. Same in the low pressure turbine section, the steam is extracted and mixed with this feed water. So here by the mixing of this steam, water temperature is increased in LP heater and HP heater. So when it is come out from the LP and HP heater, the temperature of the feed water is raised. So why we are raised the temperature of water? Because if we increase the temperature of water up to certain level, then the requirement of the fuel inside the boiler we can reduce it, and ultimately we are increase the efficiency of our plant. So now this feed water which are used is, so now this feed water is passes through the economizer. Inside the economizer, with the help of the flue gases which are already used inside the boiler and superheater, is passes to the economizer. So in the economizer, with the help of the flue gases, the temperature of the feed water is raised, and finally this feed water is come to the boiler where it is converted into steam. So this is all about the water and steam circuit. Now when the fuel is burned, after the combustion of the fuel, the ash is generated. This ash comes to the ash handling plant and finally go to the ash storage. So this is all about the ash and coal handling plant. Same thing, the flue gases is we are used inside the superheater, and economizer is passes to the air preheater where it is used to increase the temperature of atmospheric air, because if the atmospheric air is come with the high temperature, then we can say here the combustion take place efficiently. So now inside the air preheater we increase the temperature of the atmospheric air which takes the participant in the combustion process with the help of the flue gases which already used in the economizer. Then after the flue gases comes to the chimney and go to the atmosphere. So this is all about the flue gases and air circuit. So here this is the we can say modern thermal power plant looks like. There is so many component inside the power plant, but here we can understood very easily with the help of some limited components. So this is all about the modern thermal power plant. Now you can see here the major component of thermal power plant, in which we start from the coal handling plant and pulverizing plant. So here you can see this is the coal handling and pulverizing plant, in which the coal is stored and then after it is converted into small particle, and then after the impurities, some impurities are available which is removed inside this handling plant. Then after it is comes to the mill, or we can say it is pulverized and converted into very small particle. So here this is the in coal handling plant, we simply says that the coal is converted into powder form. Why the requirement of convert this coal into powder form? So here if we convert this coal into powder form, then after the coal comes to the boiler where combustion is take place. So when it is converted into very small particle, then we can say the combustion process is become very fast or rapid, and the combustion of the coal is become efficient. That's why here the coal pulverization is required. Then after we simply says that draft or draft fan. So here the draft system is used in boiler, because when the combustion, after the combustion, the flue gases are produced. So now we require this flue gases is to went to the chimney and atmosphere. So here some draft means here to create some pressure difference. So due to this pressure difference, this flue gases is go to the chimney and finally to the atmosphere. So somewhere it is a natural draft is created, but in the case where the high amount of the flue gases are produced at that time, but somewhere where is not possible to create the natural draft, at that time some artificial draft is produced with the help of fan. So here the draft fan is required to produce the artificial draft. Then after boiler, we know inside the boiler, with the help of the coal, the water is converted into steam, and the final product of the boiler is steam. Now ash handling plant, we know after the combustion of the coal inside the boiler, the ash is generated. This ash comes to the handling plant and finally go to the storage. So this is the function of the ash handling plant, to store and keep in the ash handling plant. Now turbine and generator. So here the steam which are come with the high temperature and pressure, it is expand into the turbine. So what is the function of the turbine? So function of the turbine is, when the steam is expand, at that time it's produce a mechanical work. So here what is the construction of the turbine? So we are not bother about the very constructive type, but here we can say the blades are mounted on the shaft. When the steam is strike on the blades are rotated, ultimately the shaft is rotated, and this shaft is connected with the generator. So here the electricity is produced. Now due to the expansion of the steam temperature and pressure become very low, and it is exhaust from the turbine. So now the second part is condenser. So here this exhaust steam from the turbine is come to the condenser, where it is condensed, or we can say the steam is converted into water with the help of some external cooling water. So main the function of the condenser is to change the phase of the steam at constant pressure, or we simply says that here the latent heat of the steam is removed and the steam is converted into water with the help of some cooling water. So somewhere there is a pond, river or canals are there. At that time we are used the direct water from the river at canal, then it is clean it, and then after it is passes through the condenser, where this cooling water is abstract some heat from the water, then it is passes through the condenser and come to the finally to the river other ends. So we can use the directly from the river or canal or ponds, but at the some cases where the plant does not located on the river or canal, at that time this cooling circulating water is required continuously. So here the water is come inside the condenser at high temperature, it is then come outside, its temperature is raised. So now if you want to use this water again and again, then we need to cool it. So here the cooling tower is there, where the cooling tower is to reduce this circulating water temperature with the help of the atmospheric air. So there is a, we can see the types of cooling tower and all these things later on, but here the work of the cooling tower is to reduce the temperature of the circulating water. And then after we can say the feed water heater. So here there is a two feed water heater. One is a LP heater, a low pressure heater, and second one is a HP heater or high pressure heater. Here the function of LP and HP heater is to increase the temperature of feed water with the help of the steam which are extracted from the different level of the turbine. So here LP heater and HP heater increase the temperature of feed water with the help of steam. Then this feed water comes to the economizer. So here what is the function of the economizer? So economizer is further increase the temperature of this feed water with the help of the flue gases which are come outside from the boiler. So here the flue, with the help of the flue gases, the feed water temperature is increased in the economizer. And the superheater, so superheater, we know the steam which are produced inside the boiler, it's come to the superheater where its temperature is raised again and again, and it's converted into superheated form with the help of the flue gases. And after air preheater, so the atmospheric air which are used for the combustion process inside the boiler, its temperature is raised with the help of the flue gases which are used inside the economizer and passes through the air preheater where its temperature is raised with the help of the flue gases. So air, atmospheric air which are come outside, its temperature is raised with the help of the flue gases and finally come to the boiler and take part in the combustion process. So air preheater is increase the temperature of air, and finally the flue gases is come to the chimney and atmosphere. Now alternator and exciter, here this generator or alternator with exciter is used. So here the turbine is produced and mechanical work, it is connected with the alternator or generator which rotate the shaft, and finally we get an electricity. So this is the major component of the thermal power plant, which is very easy to understood, and we can see the all about the different component in brief in our next lecture. Now we already studied different thermodynamic cycles in subject thermodynamics. So here we already studied the Rankine cycle also in the thermodynamics, but here we have to solve some problem, so some basics needs are there. So we are going with this the Rankine cycle. So we already know the Rankine cycle is a theoretical cycle on which the steam power turbine or engines are worked. So our thermal power plants are worked based on the Rankine cycle. So here you can see in the diagram, the line diagram of the main four component of the thermal power plant. So main four component in which there is a boiler, turbine, condenser and feed pump. We already know the function of the each component. Now here how the thermal power plants works based on the Rankine cycle, we have to derive the efficiency equation for the same. So now here you can see the first there is a boiler, second turbine, third condenser and fourth one is a pump. So 1 to 2 process, here you can see the 1 to 2 there is a turbine, and inside the turbine the adiabatic expansion or we can say isentropic expansion is take place and we get as an output work. Second one is 2 to 3 process, and the process 2 to 3 is a constant pressure heat rejection process, or here inside the condenser we know the steam is converted into water or phase changes take place. So constant pressure heat rejection process is take place inside the condenser. Then after 3 to 4 it is also a reversible adiabatic pumping process, or we can say it is the isentropic compression process 3 to 4 where the cooling water is we can say the cooling water is pressure is increased and passed to the boiler. And finally the 4 to 1 it is a constant pressure heat addition process. So here inside the boiler we combust the coal and heat is generated, and this heat is used to convert the steam water into steam. So here 1 to 2 is isentropic expansion, 2 to 3 constant pressure heat rejection, 3 to 4 isentropic compression, and 4 to 1 it is constant pressure heat addition process. So these four processes are consist inside the Rankine cycle. Now if we want to derive the Rankine cycle efficiency equation, then we apply the steady flow energy equation on each and every component. So now if we draw the control volume on the boiler, if we start from the boiler and we consider over here the working fluid is 1 kg, here the working fluid is 1 kg or steam is 1 kg, and we derived the efficiency equation for the same. So now first we start from the boiler. So inside the boiler if we going with the SFW equation, or we can say control volume, then we already know the water is in, steam is out, and heat is in. So energy in is equals to energy out. So energy in here water, and water is in form of fluid, so it's have some enthalpy. So here we can say HF4, and it is the fluid or water enthalpy because it is comes with the high temperature. Then after here we are added inside the boiler some heat or some coal. So Q1 amount of heat is added. So this is the two things, water and heat both are added. So we can say HF4 plus Q1 is equals to the steam is out. So steams have some high temperature and high pressure, so it's have enthalpy H1. So here this is steam out is equals to H1. So finally this is the energy in is equals to energy out, or SFW apply on the boiler. So finally we get Q1 is equals to H1 minus HF4. This is the equation number 1. Same if we apply for the turbine, then energy in, energy out. So we know the energy in, steam is in from the 1, so enthalpy H1 is equals to energy out. So work is out, WT out plus the saturated steam is come out, so it is H2. So we simply says that H1 is equals to WT plus H2. So finally WT is equals to H1 minus H2. So this is the SFW for boiler and turbine. Now we going for condenser. So if we are talking about the condenser, then we already know inside the condenser the steam is come, so it's have some energy. So we can say HF3 is sorry, this is the steam is come inside the condenser. So H2 is in is equals to the steam is reject some heat, so Q2 plus the water is come out, so HF3. So finally Q2 is equals to H2 minus HF3. Finally the feed pump, the water is in plus some work we are added to work the pump. So here we are putting some electricity to work the pump. So here WP is in plus fluid water is in, so it is HF3 plus WP is equals to the fluid water is or fluid or water is out, so it is HF4. So we simply said WP is equals to HF4 minus HF3. Now if we talking about this is the TS diagram, then we simply says that here from 1 to 2 this is the turbine, here 1 to 2 is turbine, and here we are getting some external work. So we know inside the turbine the expansion is take place, and due to the expansion the temperature of the steam is decreases. So here we can say this is the isentropic expansion process 1 to 2, and it is the turbine, and we get some amount of work as an output. Now here you can see 2 to 3, and 2 to 3 is our condenser where the constant pressure heat is rejected. So Q2 is rejected over here from 2 to 3. So constant pressure heat rejection processes take place from 2 to 3. Then after 3 to 4, and 3 to 4 is indicate the pump work, or we can say this is a pump portion where we are apply some energy, electricity, and fluid is pressurized. So here the 3 to 4 is due to the compression process some amount of temperature is increased. That's why here 3 to 4 indicates the temperature rise of the water by some amount. But here if you see the same thing from 4 to 1, here this is the boiler portion 4, 5 and 1. So inside the boiler the heat is added and temperature of this water is increases. So first when it is comes at point number 4, at that time it is in the form of water. So first when you added the heat, its temperature is raised and converted into steam. So here at the point number 5, up to that the sensible heat is added, so it is its temperature is raised. After the point number 5, when we added some amount of heat, then latent heat is added, and it's now water is converted start to convert into steam, and finally at the point number 1 it is converted into saturated steam. So 4, 5, 1 is 5, 1 it is the heat addition process at constant pressure P1. So this is the TS diagram for the same. Now here you can see here 4 to 3 is a pump. Now here HF4 minus HF3 is equals to V3 and P1 minus P2 into 100. So how it is come? So here the pump work is take place, but here the we can use the isentropic process. Here this is the isentropic compression process. So if we apply the thermodynamics relation, TdS is equals to dH minus VdP, at that time we can get the entropy of point 3 and 4 is remain constant, so TdS is become 0, so it is dH minus VdP is equals to 0, so dH is equals to VdP. So we know the enthalpy difference dH, HF3 minus HF4, and V is the volume at the point 3, and here the water is small amount of water is compressed, or we can say the water is incompressible fluid, that's why the water is not compressed, so volume is remain constant. So here it is the volume of the fluid or water at the point 3, so it is V3, and dP means pressure difference, and we know the pressure difference at point 3 and 4, and it is P1 minus P2. So that's why this is comes from the relation of thermodynamic relation, TdS is equals to dH minus VdP, which is very simple. So now if you want to use this relation for, or we can say in the relation the P is used for in bar, then multiply with the 100, so whole value is converted into kilojoule per kg. So this is all acceptably apply on these four main major component of the thermal power plant. Now we already know the Rankine cycle efficiency is equals to W net upon heat supplied. So here W net, the work is produced inside the turbine is Wt, but some work is used for to run the pump, so Wp amount of work is used. So finally we get the net amount of work is Wt minus Wp divided by Q1 heat supplied, because output upon input it is called efficiency. So our output is Wt minus Wp and our input is heat supply. Now we can take the values of Wt and Wp from the previous equation number 1, 2, and then we finally get the value of Rankine cycle efficiency H1 minus H2 minus H4 minus HF3 divided by H1 minus HF4. So this is the efficiency equation of the Rankine cycle. Now if in some cases the work required for the pump is very small, the feed pump work required is very small quantity, at that time we can neglect the turbine work. So we can modify this equation H1 minus H2 upon H1 minus HF4. So this is the final Rankine cycle efficiency equation. So it is very simple to understand, because if you learn the TS diagram and its line diagram, then you can easily got the how the Rankine cycle work or power plant work. So power plant is work based on the Rankine cycle, and its efficiency equation is this. So this is very simple. Now we can study Rankine cycle with the help of example. So it is example number 1, in which the given data is simple Rankine cycle works between pressure 28 bar and 0.06 bar. The initial condition of the steam being dry saturated. Calculate the cycle efficiency, work ratio, and specific steam consumption. So here it is very we can say simple Rankine cycle where the steam is dry saturated. So if you draw the TS diagram, and it looks like that, 1 to 2, we already know 1 to 2 is our turbine expansion is take place, 2 to 3 condenser where constant pressure heat rejection, 3 to 4 isentropic compression pump is there, and 4, 5 to 1 it is a constant pressure heat addition or boiler is there. So this is the 4 component is located on TS diagram. Now here the two pressure is there, one is a 28 bar, second one is a 0.6 bar. So here we can say the 28 bar pressure is our P1, or we simply say that it is the boiler pressure, and 0.06 bar. So 0.06 bar is a P2, or it is our condenser pressure. So here two values are given, and the steam condition is given, it is dry saturated steam. So it is dry saturated steam, so that's why it starts from the saturation curve, which is point number 1. So P1 is given 28 bar and P2 is given 0.06 bar. So now for calculation of the cycle efficiency, work ratio, and specific steam consumption, we required enthalpy, because we know at different point, because we know cycle efficiency is equals to W net upon Q1, and we know the W net is WT minus WP, and W2 and WP equation is H1 minus H2, and WP is HF4 minus HF3. So for the whole calculation of cycle efficiency, work ratio and specific steam consumption, we require the value of H1, H2, H3, H4, or we can say HF3 and HF4. So that's why for the given condition, first we find what is the value of H1, H2, HF3 and HF4 with the help of steam table. So now you can see this is the steam table. You already know and you already studied about the steam table. So here our steam is given dry saturated steam. So we have to choose the properties of saturated water or dry saturated steam is there. So here at the first point the pressure is 28 bar. So here the given data for pressure P1 is equals to 28 bar. So here you can see the range. Here not exactly 28 bar is given. Here the data is given for 25 bar and 30 bar. So with the help of some mathematical equation, you get the value at 28 bar. And if you find the value of H and S, then you can get from this table. So here the table is indicates here this is a pressure line, this is a temperature line, specific volume, saturated liquid, saturated vapor, internal energy for saturated liquid, saturated vapor, enthalpy, saturated liquid, saturated vapor and evaporation, and entropy for saturated liquid and saturated vapor. So now here you can see the value of at pressure P is equals to 28 bar. Here you get the value of H and S. So here this is the enthalpy line, 3 line 1, 2 and 3. So which value you have to choose from out of 3? So here you can see this is the at the saturated point. So here we know our steam is saturated steam, so saturated vapor line. So if the liquid, then we choose this line, but here it is the saturated vapor or saturated liquid, so saturated vapor steam. So that's why we have to choose this line, and at point at 28 bar we choose this value. So our value between 25 and 30 bar, H1 value is 2802 kilojoule per kg Kelvin. The same thing, the entropy, it is also saturated vapor line. So we have to choose this column, and we get the value between these two, 25 and 30, and its value is approximately 6.2104 kilojoule per kg Kelvin. So here we know only the steam is present. This is the saturated form, so directly we choose it. But at the point 2, or we can say at the condenser pressure, P2 is equals to 0.06 bar. So at that time the value for different components is looks like here this is the water and steam both are mixed. So we are not using directly the saturated vapor thing. So at the 0.06 bar we want to find the value of HF2 or HF3, and its value is 151.53. So this is my value of HF, saturated liquid, saturated fluid. So HF value is 151.53, and this is the for HFG 2415. So it is the value of 2415 over here. And same thing for the entropy. So this is all about the internal energy, but we have to talk about the enthalpy. So this is my value 151.53, and this is my value for HFG, and it is 2415. So this is the evaporation history. So HFG2. So here this value is indicates HFG, this indicates HF, and this indicates HG. So HF is 151.53, HFG is 2415.9, and HG is 2567.4. So this is for enthalpy. Now entropy. So entropy table you can see over here, and this is my SF. So it is 0.5210, and HFG2. So here this is my SG, not SFG2. So SG is 8.3304. So if you want to find the SFG2, then Sg minus Hf is you get the value HfG2. So 8.3304 minus 0.5210. So you get value SfG2 is 7.809. So this is the entropy at point number 2. Now volume. So specific volume, and specific volume is given over here, and here you can see this my this is a specific volume line, and here its value is 1.004 into 10 raised to 3 multiply with the 10 raised to minus 3. So in meter cube, so it is minus 3, so it is 0.001 meter cube per kg. So you get the value of the different component or enthalpy, entropy and specific volume at pressure P1 and P2 as shown in the property table, and you know how to find the value from the property table or steam table. It is very easy. So here from the given data we get the value of H1 and S1 from the steam table at 28 bar pressure, and this and same thing at condenser pressure, or we can say at pressure P2 is 0.06 bar, and so value of HF2 is equals to HF3 because this is the same enthalpy level. It is this HFG2, SF2, SFG2 and VF. So this property or these things we are get from the steam table, and you know already how to see how to calculate this value from the steam table. Now we start from the this example from the process 1 to 2. So this is the isentropic expansion process. So this is the isentropic process. So this is the entropy at point 1 and 2 remain constant. So S1 is equals to S2. We know this is the thermodynamic relation. S1 is equals to S2. S2 means SF2 plus X2 into SFG2. So that's why we know the S1. The value of S1 is 6.2104. Put this value over here. SF2 and SFG2, SF2 and SFG2 both value is here, put over here, and you get the final value of X2. So X2 is 0.728. It means that here somewhere here in which at X2 means in the condenser, inside the condenser the some 72% is steam and remaining are water. So this is the indicate the X2. X2 means dryness fraction. Same thing at point 2. The enthalpy H2 is equals to HF2 plus X2 into HFG2. Okay, because ultimately we have to find H2 and we are not getting directly the value of H2 from the steam table. So we have to use this relation. H2 is equals to HF2 plus X2 into HFG2. So here that's why we are finding out first of all X2. So HF2 we know 151.53. X2 is 0.728 and HFG2 is also know 2415.9. So finally we get the value of H2, and the final value of H2 is this. So now we have already H1, H2, HF4, HF3 and HF3. So all these values are available with us. So we can find out this WT. So WT is equals to H1 minus H2. So put H1 2802 and H2 is 1910.27. So we get the value of WT 891.73 kilojoule per kg. So this is the WT. Now WP we know HF4 minus HF3, but we already know these relations, and these relations we are already seen in the Rankine cycle as the WP is equals to H4 minus H3 is VF into P1 minus P2. From the thermodynamic relation, TdS is equals to dH minus VdP. So we get this value. So now put the value over here. VF is equals to 0.001. P1 is take over here 28 and P2 is take 0.06, multiply with 100. So if you multiply with 100 you get directly value 2.79 kilojoule per kg Kelvin. So here you get this value of WP in this way. Now W net, and we know the W net is WT minus WP. So WT is 891.73 minus 2.79. Here you can see, compare the amount of work which are produced inside the turbine is 891 and pump work is 2.79. So the value is very small amount of work is required to run the pump comparative. So in these some cases or in some example we neglect the pump work because comparatively turbine works its value is very very small. So we already see this thing in the Rankine cycle equation, where we neglect the pump work and we get the one more Rankine cycle relations as efficiency relation, and due to this reason, because you can see the practically 2.79, so value is very small. So finally W net is equal to WT minus WP, and we get the value 888.94 kilojoule per kg. Now if we want to find out for cycle efficiency, we know efficiency is output upon input, and our output is W net and input is heat supplied Q1. So W net and heat supplied Q1 is heat supplied inside the boiler, so it is H4 minus HF4 minus H1, or we can say H1 minus HF4. So W net divided by H1 minus HF4. W net we know 888.94 divided by H1 minus HF4. HF4 is 2802 and H1 is 2802, and HF4 value we get from this relation also, because HF3 is known 150.1.53, and so this HF3 is come to this side, so 2.79 plus 151.53 is equals to HF4. So this value we get H1 minus HF4, and finally we get the efficiency 33.57. So the work ratio, second thing is work ratio, W net upon WT is equals to 0.997. W net we know, and WT turbine work is also known, so we get the 0.997 is a work ratio. Specific steam consumption, so specific steam consumption is 3600 divided by W net. So 3600 divided by converted to kilowatt hour, so that's why W net is 888.94. so we get 3600 divided by 8.94 is equal to 4.049 kilogram per kilowatt hour. So here this is a very simple example, just use the steam table and you can calculate very easily, and it is maybe asked in the examination. So where the main inputs are required to understand the steam table, where the data is extracted from the same, and the pump work, where you to use this equation with relation to find out the pump work and value of HF4. So this is a very simple as compared to others, and maybe you can get the same value for we can see the same example based on the Rankine cycle. Now effect of operating condition on Rankine cycle efficiency, or we can say how we can improve the efficiency of the Rankine cycle. So here there is a three parameters which are affected on the Rankine cycle, on the Rankine cycle efficiency. The first one is a increased boiler pressure. So here we discuss the how the boiler pressure is affect on the Rankine cycle. As you know, on the graph of the efficiency versus boiler pressure, if you increase the boiler pressure up to the 166 bar, then its efficiency increases, but beyond this the efficiency decreases. So up to some level, if you increase the pressure of the boiler, you get the more efficiency. Now also you can see from the same with the help of TS diagram. In the TS diagram you can see here, by increasing the boiler pressure, which raise the temperature at which boiling take place. So here the boiling temperature is increased, and if the boiling temperature is increased, then you can say over here the heat transfer rate or average temperature at which the heat transfer take place is increases, and ultimately the boiler efficiency, or we can say thermal efficiencies, increases. So here you get the more amount of W net. So with the help of this graph we can understood the how the boiler pressure is affects on the efficiency of the Rankine cycle. Now the same thing, if we increase the, or we can say if superheating is take place, then how the boiler efficiency will be affected. So here you can see this is the graph efficiency which is degree of superheating. So here if you increase the temperature of the steam up to the superheating level, then its efficiency is improved. So the temperature of the steam is increase, then we get the more efficiency of the efficiency of the boiler. So increasing the temperature of the steam, we increases the efficiency of the boiler. So now you can see over here, If you can see, this is the TS diagram. Now here you can see this 3 4 and 3 to 4 processes represent the work done, or WT. WT means here the turbine work. So now if you up to certain T3 temperature, if you expand from the T3 temperature, you get some 3 to 4 this amount of work. But if you increase it up to T3 dash, then you get more amount of work. So here ultimately we are increasing the W net, or we can say here we are increasing the WT, turbine work output. So here by increasing the temperature of the steam, we can get the more amount of work as an output from the turbine. So here from the TS diagram you can also see the same thing, how we can increase the efficiency of the Rankine cycle by reducing the condenser pressure. So what is the condenser pressure? We already know. Now here you can see from the graph efficiency versus condenser pressure. So here by lowering the condenser operating pressure of the condenser, if you reduce the condenser pressure, the efficiencies will be increases more and more. So here the pressure is decreases. If the pressure is decreases, then the efficiency is increases. Here now you can see why this is the happening, because if you lower the condenser pressure, automatically lower the temperature of the steam, and thus the temperature at which it rejected. So here if you reduce the temperature, if you reduce the pressure in the condenser, then its temperature, heat rejection temperature is reduces. And as well we can see from this TS diagram, you can see over here, this is the 1 dash and 4 dash and 1 4. If you 3 to 4 is the expansion. If you reduce this up to first of all we have start with the 3 to 4, so we get this amount of heat rejection is take place. But if you reduce from 3 to 4 days, then this amount of, so we get more amount of work. If you reduce the pressure 3 to 4, small amount. If you reduce more 3 to 4 days, then we get more amount of work. So we get 1 days to 4 days up to here, this is the more amount of work we can get. So W net is increases. So here if the expansion is take place in the turbine and inside the condenser pressure is reducing very low up to the 4 days, then we get the more amount of W net as an output. So this is the 3 things which are effects on the Rankine cycle efficiency, and we can understood these things with the help of TS diagram and its efficiency versus different component diagram. So it is very simple. Now we see the cogeneration power plant. So what is the cogeneration power plant? Actually the cogeneration power plant is nothing but it is the combined heat and power plant. So heat and power plant. So here if you define the cogeneration power plant, then it is defined as sequential generation of 2 different form of useful energy from the single primary energy source. So if we take the example of our power plant, then if you produce the steam, and this steam is used for typically mechanical energy and thermal energy. So here typically in the boiler you can see the steam is generated which is used to produce an mechanical energy and thermal energy both. So how we can improve our or we can extract the more amount of energy from the steam. So this thing we can achieve by the cogeneration power plant. So if we see this thing, then if you see this is the block diagram in which you can see if you apply the fuel, and the fuel, so engine or turbine is some more amount of we can say here the fuel is applied, maybe use the gas turbine power plant, or maybe you can use as a some other power plant where engine if there is a gas turbine power plant, then we can say here the combustion is take place, and due to the combustion hot flue gases are produced which are strike on the turbine, and turbine is rotated. This turbine is rotated, this turbine is connected with the generator or exciter, so where the electricities are produced, and this electricities which are used for building or a facility, and we can say at the homes or grid. So here you can see the one application from the single source. Here the single source of energy is a fuel where the electricities are produced first of all. Then after the flue gases which are used inside the turbine, this come out, and this exhaust gas which use in the heat recovery unit, we simple say the boiler, where heat recovery units, in heat recovery the water is added. So water is added, then this water is converted into steam or hot water. So this steam or hot water we can use for different purposes, like we can say for cooling and heating purposes, we can say in the process industries. So if you want to use in cooling and heating in the building, then we can also use it. So here, from the single source of energy, primary single source of energy, we can use the different ways. So due to this, if we elaborate it, then we can say here the typically mechanical energy and thermal energy. From the single force we are producing both things. So mechanical energy may be used, here we know the mechanical energy we use for to produce an electricity by use of motor, compressor and pump and various pump. But if we talking about the thermal energy, then the thermal energy here, it is produced the steam, which are if we use either for direct process application. For if you use the for direct process application, means here we are producing the steam, and steam is used for the process industries like sugar mill, textile mill, paper mills, etc., in which the steam is directly used or is a part of the manufacturing process. But if you use the indirect processes like hot water, hot air for the dryer, chilled water for the process of the cooling. So here you can see here in the building, you can, if you want to heating it, if you want to cooling it, then this thermal energy we can use it. So here from the single primary source of energy, we can produce the more amount of, or we can utilize the more amount of energy from the source. So this is the main we can say principle of the cogeneration power plant or combined heat and power plant. So now if we think about its efficiency, then in the conventional power plant, if you think there is a no only the fuel is applied in the boiler and it's produce an steam, and this steam is strike on the turbine and electricity is produces, and this steam is condensed, and then after it is used further. So this is a very conventional, there is a four main component and it is used. So there is a conventional power plant, there is only the 45% of energy is utilized. So here we can see there is a amount of heat is generated inside the boiler, there is only 45% of this energy is utilized, and rest of energy is wasted, because the energy is wasted in form of, we can say in form of flue gases. The flue gases which are produced inside the boiler, we are utilized only the 45% of energy of the flue gases, and remaining the energy which is exhausted with the help of chimney to the atmosphere. So 55% energy we are not used from the flue gases. So this amount of energy we are lost in the conventional power plant. So what we can do, how we can use this energy further of the flue gases energy with the flue gases. So here our solution is the cogeneration plant, in which we can utilize this flue gases further to increase the temperature of water and convert it into steam, and these steams or hot water we are utilized for our different purposes. So in this, the total amount of energy from the flue gases we can use 18%, and only the 20% are wastage. So the amount of heat is generated inside the boiler in the which are content with the flue gases, we are utilize 80%, because it is used in the two stages. One stage is where mechanically we are used it, and in the second stage is thermally we are used it. So in the thermal and mechanical, in both way we are utilize it, and more amount of benefits from the flue gases we can use it and get the more efficiency from the plant. So this is a very simple concept of the cogeneration power plant. Now if you see the types of the cycle or types of the power plant, then it is the topping cycle power plant and bottoming cycle power plant. So what is the topping cycle? In this, the combined heat and power plant, electricity is generated first, and waste or exhaust steam is used for heating purpose or any process. So here in the topping cycle, the steam which are generated, it is used first for electricity production. So we can say it is used first for in the turbine, then after this exhaust steam from the turbine, it is used for different purposes, like we can say heating of buildings and others. So here our main aim is to produce, your main in the topping cycle, the main aim of the steam is to produce an electricity. So first aim is to produce an electricity, and remaining heat which are available with the steam is used for heating of the building and heating of the water and other processes. So in the topping cycle, main purpose to produce electricity, secondary purpose is to increase for process heating and all these things. So now this is all about topping cycle. Now if you talk about the bottoming cycle, in the bottoming cycle, the excess heat from the manufacturing process is used to generate the steam. So here the different use of the steam is different, or we can say the here when the heat which are used inside the manufacturing processes, which excess, or we can say more amount of heat which are produced in the manufacturing process, and this heat is used to generate the steam, and this steam is used to generate the electricity. So here the main purpose is not to produce an electricity. Here the main purpose of the heat is to use in the manufacturing process, and remaining amount of heat which are wastage, or we can say the excess amount of heat which are produced during the manufacturing process, this heat is used to generate the steam, or ultimately to generate the electricity. So this is the difference between the topping cycle and bottoming cycle. So in the first and second one, the very clear idea about the topping and bottoming cycle. Now if we need of the cogeneration plant, what is the advantage of the cogeneration plant? So here we know, here we are improve the efficiency, because we ultimately use the steam use the flue gases energy up to the 80%. So improve the efficiency of the plant, reduce the air emission, because we use the more amount of energy from the flue gases. That's why we require very less amount of the combustion, and if we less amount of the combustions, then we required very less amount of the coal, and ultimately we have to reduce the combustion emission and air emission. So here the particularly the nitrogen oxide, sulfur, because burning is less, coal is not required to burn because more amount of energy we are used. So that's why the nitrogen oxide, sulfur oxide, mercury and carbon dioxide will be generated very less amount. So this greenhouse effect we can reduce this. Now we can reduce the cost of production and improve the productivity, because we are use the most of amount of heat. So we can improve these things. Cogeneration save the water consumption and water cost. So here we can see the steam is used in both the situation. First situation where we are using the for purpose of electricity production, and second uses for the process plant. So in both the system we are using the same water. So requirement of the water is decreases if this both the processes take place at the different place or different way, then we require the more water consumption, and that's why the water cost is increases. So by using of the cogeneration system, we can reduce the water consumption and ultimately water cost. So now the cogeneration more economical compared to the conventional, because we know the efficiency we get the 80%. So we utilize the heat which are produced in the boiler, we utilize up to 80%. Only the 20% is we can say lost. So that's why it is more economical than other conventional power plant. So it is all about the CHP and cogeneration power plant. Now selection of site for thermal power plant, or we can say where the thermal power plant is located. What is the sites where we can so it is located. So which facility should be available for the thermal power plant. So first we can say the transportation network. So we can say here there is a easy access of the transportation facility for the thermal power plant, because there is in thermal power plant there is something which are daily needs, some we can say fuel, water and all these things. So your plant should be located near to the highways, rails and airports, so we can easily transport the requirement daily needs with the help of this. So transport network should be easily available during this all this thing. Second one is the power transmission network. So your system, your plant should be located in such a area where power transmission should be easily done, because after the completion of the construction of the site, then the power is produced. This power is transmitted to the region where it is needed. So there is some area, we can say there's no forest area, no hill area, where we can say we are not easily transport the facility or power, and that's why the power station should be located at that area where this constraint should be negligible, or we can say eliminated. So power transmission network should be easily located, and we can transmit the power should be required area as easy as possible. Then we can say geological and soil type. So your soil where, or your area where you locate your power plant should be should be made up with the oil and rock layers, because the soil is not made up with this such a layers. Then if we made up with this we can say very soft, then it does not sustain the weight and vibrations. So your power is located at that area should be construct, or we can say it is made up with the rock layer, so it can easily sustain the weights and vibrations which are produced the different components of the power plant. So this is the geological and soil type benefits must be there. And then case topography, it is the proof that high elevation has negative effect of production of the efficiency of the gas turbine power plant. So topography is very important, because you can't locate the gas turbine power plant at high elevation, because if the elevation is high, the air becomes low pressure. So due to the low pressures, it become very thin, and that's why we can't use this air for the power production, or we can say the efficiency of this gas turbine is reduces. So this is the topographically advantage should be there. In addition, the changing of the sloping area into the flat sites construction for the power plants needs extra budget. So if you locate it at the hill area, or we can say very height, at the heighted area, at that time if you transport something, then you should make some roads, and this roads should be done by making the slope area to the very flat. So extra budget should be needed to construct the road in this height area. So this is the topographical benefit must be there. The area should be very flat, and it is we can say on the sea level, so we can easily get the air and all requirements. Then we can say earthquake and geological faults. So even weak and small earthquake can damage many parts of the power plant intensively. So your plant should not be near to this area where frequently the earthquake or the shocks are continuously run, because it may damage your different components of the plant intensively, and that's why you should must stop the plant and maintain it. So it's very not easy to do such a things continuously. So your area is very far away, or we can say your plant should be located in such a way that there is no effects of the earthquake and other geological faults. Then after we can say water resources. So we know the for thermal power plant, the continuously waters are required. So your plant should be located near the bank of river and sea, so we can easily extract the water from it, and easily we can run our plant. So water should be sufficiently available. It is must require. Environmental resources, so far enough from the national park, wildlife and protected areas, etc. Because if it is, we know during the combustion of the fuel inside the power plant, there is so many greenhouse gases are produced, or we can say some carbon dioxide, sulfur dioxide, this such a damage gases are produced, and this is effects on the wildlife, humans and other national parks, trees even. So should be locate your plant away from this such a areas. Maintain the distance between this life and plant. Then after pollution centers, so enough distance from the pollution centers, because the plant we can't locate near the cities, because where the human beings are there. So if the pollutions are created much more and it is goes to the atmosphere, this affects the health of the humans being. So we should maintain or manage the distance between the human cities areas and the plant. So it's a very important thing. So pollution center should be such a distance will be maintained. Climate parameters such as temperature, humidity, wind direction, speed affects the productivity of the power plant. So this is the parameters, environmental parameters, which we say continuously affects on the power plant. So should we measure this thermodynamical parameters, or we can say these parameters, before start or before going with this construction of the plant, because it is much more affects on this on the working of the power plant. So before going to construct this parameter should be checked, and it's not up to the we can say going to be beyond the limit. If this, then we can choose such a area where so much temperature, humidity and wind is flow, because it affects the working of this power plant. So this is the few list of the parameters which affects on the construction and working of this power plant, thermal power plant, but we can see the much more. So this is all about the site selection for the power plant. Now if we think about the recent development of power generation, or we can say all India installed capacity in megawatt for power generation as on dated 31/3/2017. So here if we talk about this, then we simply says that the thermal power plant based on the coal, gas and diesel, or with the region, or we can say by the different areas, we can say the state government, private government and central government. So state government and private sector and central government which are installed with installed capacity is available over here in the coal, in gas and diesel and grand total of the thermal power plant. So by the different the state government, the capacity of the thermal power plant is 7230.38 megawatt. Same thing we can say the private sectors, which is the installed capacity or 84196.68. Central governments have a 61825.83. So total amount of electricities which are produced from the thermal power plants is 218,329.9 megawatt by the different region, by state, private and central government. Same thing, the electricities are produced with the help of nuclear, or we can say nuclear power plant, it is 6780. Same thing for hydro energy, we can see total amount of 4478.42, and renewable energy sources, that is the 50,018 megawatt powers are produces with the help of renewable energy sources, which are we can say produces by the state and private sector. There is no involvement of the central government. Same thing, if you see, this is the grand total of the region wise. So total amount of electricities we can produce in India, or installed capacity of India in power generation is 319,606.31 megawatt. So this is all about the power plant capacity in India up to the dated on 31/3/2000. This data is captured from the www.cae.nic.india reports on dated 31/3/2017. Now in this slide you can see in form of the pie chart, there is a thermal power plant where the electricities are power is generated, or electricities are produces. The 88% electricity are produces from the coal, 12% are produces from the gas, and maybe approximately small amount of electricity are produced with the help of diesel power plant. Same thing, all India installed capacity in megawatt for the power station. So 68% electricities are produced in the thermal power plant, and we can say small amount 2% electricities in the India are produced from the nuclear, 14% are produced from the hydro, and 16% are produced from the renewable energy sources. So this amount of the energies are produced with the help of different resources in India. The same thing you can see the region wise, the power generation in India, then the 42% is electricity is are produced by the private sector, and 33% are produced electricity by the state government, and only 25% are produced by the central government. So here this is all about the power generation capacity and power generation, about the power generation in India up to the 31/3/2017, and this is the taken from the central government side, and you can see this is the scenario in India. So this is all about the thermal power plant. Now, so this chapter is completed over here. Now you can see this is the highlights of this video lecture. In the first, we see the modern thermal power plant layout, what is the different component of the layout. Second one, then the Rankine cycle, how the power plant works. Then method to increase the efficiency of Rankine cycle, how we improve the efficiency, or which things which affects on the efficiency of the thermal power plant. Then after cogeneration plant, what is the CHP cogeneration, how it is works, what is the type, then the different site selection, how the where the power plant should be located, which parameters which affects on the construction, and we can say working of the thermal power plant. Then the recent development of the power in India, in which the power plant is how many amount of power is produced or installed capacity in India with the help of the different data from the government side. So this is the all about the this is the first chapter of the modern thermal power plant. So thank you very much for seeing this video. Thank you, and thank you all.